Today we're going to talk about what happens when our velocity is no longer held constant. Say you have a car that is initially traveling at 12 meters per second. Now you step on the accelerator or gas pedal, and sometime later you're at 25 meters per second. We can see that the velocity has changed. A change in velocity is called delta V. The delta is a Greek letter that stands for change. Whenever you see it, you should take the final value and subtract the initial value. Since velocity is a vector, we must keep in mind the direction of each of the vectors we add or subtract. In this case, both instances are going in the forward direction, so they stay positive. And we find in this case that the car sped up by 13 meters per second. Of course, the car is not going to speed up instantly. This takes place over a period of time. You might hear in a car commercial, they brag about a car going from 0 to 60 in 3.2 seconds, meaning the car takes 3.2 seconds to go from a still parked position to 60 miles per hour. Mathematically, this is saying our delta V happens over a period of time. This rate of change of velocity is the quantity we call acceleration. We use a lowercase a to indicate acceleration in physics. This gives us our first of the three major kinematic equations. Acceleration is equal to Vf minus Vi all over the time it took to change the velocity. Notice that this is a vector equation, so acceleration has both a size and a direction. When we say something is speeding up, we are saying that the acceleration is pointing in the same direction as the initial velocity. If the initial velocity is negative and it's speeding up, the acceleration is pointing in a negative direction. This is just like if you're driving south on a highway and hitting the gas. The term slowing down refers to when acceleration and the initial velocity oppose each other, or point in opposite directions. So if you were driving southbound, your velocity is pointing towards the south, and you are slowing down, your acceleration is pointing to the north. To illustrate this, I'm going to give you three examples. Example 1. Say you start at rest. Maybe you're at a stoplight, and the light turns green. So you zoom up to a final velocity of 26.8 meters per second, and this takes you approximately 4.60 seconds. What is your acceleration during this time? To find this, we're going to use the acceleration equation. A is equal to Vf minus Vi divided by time. For this case, 26.8 meters per second minus 0, all divided by 4.60 seconds. This gives us an acceleration of 5.83 meters per second squared. Notice that the units of acceleration are different than the units of velocity and speed. For our next example, let's talk about the situation that we often encounter when driving. We're driving along the road, maybe we're going a little faster than we should, and we see a police car on the side of the road. We decide to tap on the brakes slightly, causing an acceleration pointing backwards in the opposite direction, which slows us down to a more reasonable velocity, say perhaps 26 meters per second. So what is the value of our acceleration? Well, we start off with our acceleration equation. A is going to be equal to Vf minus Vi over t. But we haven't figured out how long did we hit the brakes for? Well, maybe we didn't want to draw too much attention to ourselves, so we slowly tapped the brakes for 1.85 seconds. Now we have all the values we need, we can plug them in. So Vf is the smaller number, 26 meters per second, and we subtract from that the initial velocity of 33 meters per second, all of which is divided by 1.85 seconds, which gives us a negative 3.8 meters per second squared. Now it's always a good idea to double check your answer at the end of a problem. Does it make sense? Well, here we have a negative sign, and our initial velocity was in a positive direction. So the two oppose each other, and we slowed down, so our number got smaller. Everything seems good. Let's move on to example number 3. For this example, let's move in the opposite direction. So our v initial is a negative 15 meters per second. What would happen if we experienced an acceleration of a positive 2.5 meters per second? And this occurred for a time of 7 seconds. What would our final velocity be in this case? Well, here we have our acceleration equation that I need to rewrite in order to find Vf. If I solve this for the final velocity, Vf is equal to the acceleration times time plus whatever my initial velocity was. This is such an important kinematic equation, it is worth remembering. For this case, Vf is going to be equal to 2.5 meters per second squared times the time we were accelerating for, 7.0 seconds, plus our initial velocity, which in this case is a negative 15 meters per second. Be careful with your minus signs here. When you calculate this, you will get a positive 2.5 meters per second. This means our car is now going in the opposite direction. Essentially, it made a U-turn. At first, our acceleration and our velocity were opposite, so the car slowed down. And then, as it continued moving, the acceleration was positive, it became positive, and we were speeding up. As a reminder, velocity and acceleration are vectors, so the direction is extremely important. So always double check your minus signs when you plug into your calculator.